Hello students, welcome to Lecture 3. In this lecture we will continue the previous topic which was focused on introduction to BCI systems or general overview of the BCI system. Here we will briefly stop about the challenges of BCI classification problem and also BCI decoder. Well, in previous lectures we have seen different components of the BCIs. We talked about different ways of generating the brain data and different measuring modalities that allows us to measure the associated brain data that relates to the mental state of a user. And then today we will briefly discuss decoding, given some data, how we can decode, and later for different applications. So, we have two options in order to build BCI. So, first option is to train the user. Let me turn this on. Okay, yeah. So, to train the user using neurofeedback to generate a strong predefined signal with a voltage of possible 0.5 microvolt over CZ. CZ is central location of one electrode. So this is similar to one of the applications that we have reviewed, where subject learns to regulate some brain activity patterns. However, it will take several months until the BCI user can train his brain to generate strong signal. Second option is train the machine to learn user-specific signal properties. So here, given data, we train machine to learn from data to decode users' intended mental state. So we use machine learning and classification, in particular classification algorithm, to automatically decode what's called neural code for each different subject or participant. So machine learning allows us to shift the burden of human learning, right? So instead of training a human to generate some signal to control BCI application, we can train the machine. So it will, in some specific case, just takes a few minutes to recognize relevant features of the brain, rather than weeks, months of training a participant or BCI user to modulate predefined features. So we just let the system, the machine, learn itself, no intervention from experts required. Well, we can take a look at general flowchart here, different components of the BCI or BMI system. User generates strong brain signals, and we have some activation patterns in the brain, which is recorded using, let's say, some electroencephalographic device, so EEG. Then we use those data to train the machine or machine learning algorithm. First, we construct we had to do some specific pre-processing, and then we can train, let's say, a decoder. And then decoder will exert output for different application, BCI application. It can be for communication, BCI spelling, or environmental control. So turning off the lights and off, or some other applications based on the need, or locomotion or movement control. And feedback is important part of the entire flowchart. So user needs to see whether his intended mental state has been accurately decoded by the classifier. We can have different feedback: visual, auditory, haptic, electrical, thermal, tactile, or vibration. Let's ask again the same question: how does a BCI work? Well, in fact, it has been demonstrated about 25 years ago that the BCI is possible. When building a BCI system is possible. For instance, in 1988, the first ever BCI-based communication device has been used or developed by Farwell and Dungeon. They use P300 waveforms and electroencephalographic data to control, to spell out some letters and characters. It's quite a long time ago, right? And even current days, these P300 based BCIs are very, very popular and widely used in real world applications. And later, Bierbaumer, a professor at University of Tübingen, Germany, was the pioneer of the BCI based on slow cortical potential. So slow cortical potentials are the signals that can human learn to generate or to control. So we can train the human to generate specific patterns in EEG data. And while in P300 visual speller, we have external stimuli, it's exogenous type BCI, this is endogenous. Well, later, even more interesting, during those period of time, Professor Furtscheller has developed mu-based BCI. Well, BCI that uses as input data that corresponds to imagination of limb movement, moving right arm up and down, left arm or foot. We can see that a lot of different application has been demonstrated in past, about 25 or 30, almost 30 years ago. So the question is now, so what have we been doing since then, since those 1988s? So to answer this question, let's take a just quick example about a science fiction ideal BCI. So let's think back to the science fiction ideal BCI. They are very fast, accurate, and intuitive. But this is our ultimate goal. We would like to have a BCI look like in those Hollywood movies. And another thing is that building a demo BCI is very easy. All those videos that I have shown, most of the cases are successful attempts. So those are basically very good BCI for demo, but may not be usable or practical outside the lab environment. So building a usable BCI is hard. So as, let's say, with speech recognition system, so in order BCI to be useful, we must have fast BCIs, okay, that gives us one comment in less than 3 seconds per binary decision. So the BCI should be fast and accurate, of course. The classification accuracy should be at least higher than 90%. So nowadays, state-of-the-art BCIs, let's take as an example the P300 based BCI or ERP based BCI. They can generate decisions every 6 seconds. So it's quite slow yet. And then they're not as accurate as 90% or above in most cases. So this arrow goes here further. So it should be easy to use, very important. No expert knowledge or human intervention. So it should be just like some gadget or some some device that you just put on your head and then start using it. And fast setup, of course, is another important criteria. So we need to have a BCI system that should be right, just plug and play kind of device. So no long training times, and for the user or the decoder both. And generally should be applicable for everyone, because BCI is nowadays still very subject specific. So the BCI that works for you has been optimized for you, for example, will not work on me, because we have different brain patterns. So why is it so hard to make the BCI useful? Well, one of the problems with the non-invasive BCI or brain-machine or brain-computer interfaces is that the data that we acquire from the brain is buried in noise. So they have very poor signal-to-noise ratio. For instance, if we compare here example of the event-related potentials, the brain signal patterns between non-target and then target stimuli, we see the average ERP response is quite weak. So in the background we see a lot of trials. They show some different distribution. It's visually it's hard to say that there is some pattern. Only after averaging hundreds of trials we can see some trend. While in target case, okay, so red here represents some individual case of brain response to a target stimuli, and average information here. So in general, the problem, one of the biggest problems, challenges of the BCI is the data that we collect from outside the scalp using EEG or MEG is has a very poor signal-to-noise ratio, and is affected by various kind of noise sources. So device-related noise or heartbeat, EMG, eye blink, other neural sources. So I could roughly say that 70% of the data that we collect is noise. Only 30% contains the signal of interest that corresponds with the mental intent in BCI. Another problem with a non-invasive BCI is they have low spatial resolution. Well, this applies to EEG and MEG. Most likely, in most cases, EEG-based BCI. So if you take sensors, okay, electrodes, that has been placed on the human head and collected data, and take the correlation. This is correlation matrix. You see that the sensors are very highly correlated. So this is also called as spatial blurring. So we cannot separate data between each different electrodes. For instance, so if you take a look at the electrode 60, it is very highly correlated with other channels electrodes, which this is a bad news. In ideal cases, we want each electrode to represent clear information about the mental state that is not highly correlated with a neighboring electrode. So this brings us a low spatial resolution, so we cannot pinpoint exactly where, in which channel, in which part of the brain some interesting activities happen. This is due to spatial propagation effect. So from brain up to scalp, we have several layers that needs to be propagated. Another known problem is one of the biggest problems are intersubject and intersession variabilities. So these are examples of EEGs, electroencephalographic data, in the form of topography. So color-coded amplitudes, let's say. And each cross here denotes one channel. We will see a lot of these kind of topographic images from now on, and you should get used to seeing, learning how to interpret them. So here we have nose, human nose, eye somewhere here, right ear, left ear. And each cross represents electrode. And the color coding is the value of the amplitude or the power of the signal at that specific electrode. And we have special interpolation techniques that will interpolate the color distribution here. So the data here, this top row shows us the data collected from the same subject when he imagined moving his left arm across 5 different sessions, experimental sessions. What we can see here is that even so the same subject, the generation of brain data is highly variable, right? So between sessions we see different patterns. For instance, session 4 is very different from other sessions. The generation, the color distribution, topographic distribution. Session 1, okay, is very good. Looks very localized, and is different from others. So this is related to intersession variability. This is bad news because in machine learning, we assume that data is generated according to some fixed distribution, fixed but unknown distribution. In other words, identically independent distribution. If that assumption is violated, your classifier or machine learning algorithm will fail. So you train on data based on session 1, day 1, and that machine learning algorithm will not work on other days' data because the distribution is very different. And that makes a BCI very impractical. So one solution could be you train, you optimize your BCI on a daily specific data, but that is not what we want eventually to avoid any kind of inconvenience. If you look at the right-hand imagination data across 5 different sessions, we see even some chaotic, very random behavior, right? So session 1, okay, some data. 4 is very different. It's also very hard visually to localize same patterns. Okay, it would be ideal, well, these data generated during this imagine would be same, remain same, so that the machine learning algorithm will not fail, will be providing us good accuracy. So apart from that, these are called intersession variability. We also have intersubject variability. So intersubject variability is that the data that is generated by your brain is different from mine. Well, if you take 10 students and acquire data from 10 of them using same left and right hand imagination protocol, the data will be very subject specific. Well, the data of EEG is not as different as like fingerprints, if I want to give as analogy, but very different. Your data is different from mine. So we cannot have a BCI system that will work across subjects easily, right? For example, in speech recognition systems, even so we have different accents when we speak English, right? They can still learn the unique properties of the features of the speech signal and accurately decode what we are speaking. So it's Alexa or Google or some other systems. If you go a bit detail, so we have inter-trial variability. That means, you know, the data generated at each trial is very different, even from the same subject. That puts another very huge difficulty in building a practical, stable BCI. Right? So for instance, here you have data collected at central channel, at the peak of your scalp. So each individual time series corresponds to one trial, okay, from the same subject, while imagining or while performing same BCI task. What we see here is they are very different from each other. Okay, so trial 1, trial 2, 3, 4, 5, 6. This leads again to the failure of previously functioning BCI, because one of the main components of BCI is a decoder, and decoder will fail in decoding if the underlying distribution is very different. Underlying distribution of the data is very different. That's why over the last 30 years, people have been trying to address this inter-trial, inter-subject, inter-session variabilities, as well as trying to make this spatial resolution increased or improved. So the final component of the BCI is the output. So once we decode the mental state of the user, we can pass that decision to control some output application. That could be computer cursor or spelling application, or controlling a wheelchair or robotic arm or exoskeleton. It depends. But the core part is about decoding accurately the human mental state. The other part is a simple engineering programming task, depending on the user needs and the application. Despite those challenges, why BCI has become so popular suddenly? Right? There are two reasons. First is in algorithmic and then hardware developments. For instance, we have very advanced algorithms or advances in signal processing and machine learning field. We are living in the era of, let's say, AI and deep learning, and also a lot of advanced signal processing algorithms have been designed that is well enough to make good decisions on a very little data. So let me fix this. And also we have hardwares nowadays which became cheap enough to run fancy heavy algorithms, and also recording hardware, EEG system, that's cheap enough again for many people, including customers, we can afford. So we can buy EEG, portable EEG recording system as low as for, let's say, $200 roughly, right? So let me list the challenges, one of the main challenges in BCI research. Okay, one of them is increasing the speed of the BCI system. So this is related how fast you can generate a command. And second one is increasing the accuracy. So how accurate your BCI should be 90% or above the accuracy. We also have some problems related to BCI illiteracy. Okay, addressing the problem of BCI illiteracy. So BCI illiteracy is a problem where around like 30% of populations are unable to use BCI, regardless of how accurate your BCI system is. And number 4, and then this BCI research focus on designing BCIs for BCI illiterate populations. So Number 4 is reducing calibration time. Rapid, for example, user adaptation, cross-subject generalization. So we need a BCI without calibration. Nowadays, most BCI involves recording user data and then calibration or training the algorithm and then move into the real-time use cases. And number 5, let's say continuous self-paced operation is another challenge, another interesting problem that most BCI researchers work, which focus on the designing BCI that is independent of any kind of possible stimuli, and it can work as natural as those ideal BCIs. Another problem is adapting to non-stationary to BCI signals. In this case, right, we have inter-session variability, inter-trial variability, or inter-subject variability. Number 7 case, exploiting neural plasticity user learning to improve performance over BCI. Well, one of these problems could be combining machine learning with human learning, right, to improve general performance of BCI, because human can also learn somehow to generate some specific patterns in the brain. And finally, some of them, as ease of use, make intention encoding more direct, more literal, more intuitive. And finally, among all others are these. So most BCI, 70% of BCI research is based on increasing speed and accuracy. 70% is based on my own observation. So roughly around 70% of research is based on increasing speed and then accuracy. Let me summarize these overall introductory lectures to BCI. So we have discussed that the BCI communicate user's intention without the use of peripheral nervous system, right? So BCI use only data coming directly from the brain in their definition. So if you use some other signal such as EMG, then it's not BCI anymore, but BCI plus something. Then we also discussed about two different types of BCI. First one, stimulus dependent, and then second one was stimulus independent. We also discussed them as exogenous and endogenous type of BCI. Intention encoded in selection. Okay, so BCI design problem is to make it faster, reliably, easier, more accurate, and user-friendly, practical. So we have two approaches to doing these improvements. Improve the encoded signal strengths by optimizing the mental task. This is more about experimental BCI research, okay? Or improve the signal decoding by using advanced signal processing and machine learning. So in this case, given data, we come up with novel signal processing and machine learning algorithms to improve the signal decoding classification. While in this case, come up with a novel experimental paradigm that will allow us to improve signal strengths and use simple algorithms for decoding. Well, if you have any questions, you can send me email or write in the Telegram group. This lecture was was short, and in the coming lectures we will continue and delve into more details of each. For instance, what is ERP-based BCI? what is EEG, and some other BCI paradigms. And we will also see some examples of decoders, signal processing algorithms. Now I have one assignment. On Moodle you can find this PDF file that I have uploaded, right? And then this PDF is called as Brain-Computer Interfaces, a Gentle Introduction. If you open up, right, this is very, very useful complementary information to the lectures up to now, right? So lecture 1, 2, 3. So I highly recommend you to read the entire PDF file to gain some additional information about the BCI and its application and different types of the BCI. And at some point later I will ask you to make a presentation regarding each specific topic here. This paper is a little bit outdated, but still carries a core concept used in BCI in modern days. I think that's it for today. I will see you in the next lecture online.